In 2014, a team of robotics engineers at Harvard faced a problem that shouldn't have been so difficult. How do you make a group of simple robots build something complex without putting one robot in charge? The answer didn't come from another robotics lab, it came from an insect that had already solved the problem millions of years earlier. You're looking at one of them now, not a king, not an architect, just a worker smaller than a grain of rice. It carries a single pellet of wet soil toward a wall it will never see completed. Long before this mound is finished, that worker will be gone. It might die, it might simply grow old. Either way, another worker will quietly take its place, carrying another pellet to almost exactly the same location. The construction almost never seems to pause. Workers come and go, generations pass, and the mound keeps growing as if every individual were replaceable, because they are. Now imagine shrinking down until you're standing exactly where that last pellet landed. The wall beside you stretches upward. The tunnel ahead bends with impossible precision. Warm air and gases rise through hidden shafts. Cooler air is drawn in through lower passages. Over time, the entire mound moves air in and out like a living lung. No blueprints, no construction manager, no control room. And somehow every new pellet ends up exactly where it needs to be. I've read a lot of research on collective intelligence, and this is the moment that completely changed how I think about leadership. Because if nobody designed this, who did? For a long time, it was easy to imagine the Queen held the answer. Human civilizations have presidents, companies have CEOs, armies have generals. Surely a termite colony must have someone giving orders too. Except the Queen almost never leaves the royal chamber. She doesn't inspect tunnels, she doesn't direct workers, she doesn't decide where the next wall should go. Her primary job is astonishingly simple. She lays eggs, that's it. When researchers study how termites build, they notice something surprising. The workers weren't waiting for royal instructions in the first place. They kept building because they already had the only information they needed, what was happening immediately around them. That's when biologists realized they had been asking the wrong question. The mystery was never who is leading the colony. The real mystery was much stranger. How can thousands of individuals build something no single one of them understands? The answer wasn't hidden inside the termites, it was hidden between them. Every worker follows only a handful of simple rules. Pick up a pellet, sense the shape of what's already nearby, respond to chemical signals left by other workers, place your pellet where those local conditions tell you to, then repeat, that's it. No termite knows the finished shape of the mound. No termite carries a blueprint. No termite can step back and admire the architecture. Each one experiences only a tiny piece of the world around it. And somehow that tiny piece is enough. Scientists have a name for this: stigmergy. It's a form of coordination where individuals communicate indirectly by changing their environment. One termite places a pellet, that pellet changes the environment. The next termite reacts to the pellet. Its pellet changes the environment again. The process repeats thousands, then millions of times. The mound isn't built because anyone understands the design. The design emerges because every worker keeps responding to what the previous worker left behind. That idea caught the attention of robotics engineers. In 2014, researchers at Harvard, led by Justin Werfel, asked a remarkable question. What if robots stopped trying to think like engineers and started behaving like termites instead? They built a group of simple robots. None of them carried a full blueprint in memory. None could see the entire structure. None could tell the others what to do. Each robot knew only its immediate surroundings and a small set of construction rules. From an engineering perspective, it sounded almost too simple. Then they switched the robots on. One block became 3, 3 became 10. Walls began to appear, ramps formed. Entire structures slowly emerged from dozens of tiny decisions that no single robot understood. No supervisor, no central computer directing every movement. Just local information repeated over and over again. The project became known as Termites, and it demonstrated something engineers had struggled with for years. Sometimes the smartest system isn't the one with the smartest individual, it's the one with the smartest interactions. That realization reached far beyond robotics. Researchers began exploring the same principles for search and rescue robots, navigating collapsed buildings, for autonomous construction in places too dangerous for people, even for proposed future missions to the Moon and Mars, where long communication delays would make constant human supervision impractical. The termites weren't solving a construction problem, they were solving a coordination problem, and once you see that, you start noticing the same pattern everywhere. The more I studied collective intelligence, the more I realized something uncomfortable. Not because the science is complicated, because it's personal. it means being irreplaceable was never guaranteed. Not for a termite, and maybe not for you either. We've been taught that every successful system needs someone at the top. A CEO, a commander, a chief engineer, a mastermind holding the entire plan together. Nature keeps telling a different story. Your brain works because billions of neurons follow simple electrical rules. No single neuron understands your thoughts. The immune system protects you without a commander directing every white blood cell. Flocks of birds twist through the sky without a lead bird choreographing every turn. Schools of fish evade predators without a traffic controller. Again and again, complex order emerges from simple interactions, not from a central authority. That doesn't mean leaders are useless. Some systems genuinely require leadership, long-term planning, and centralized decisions. But nature reminds us that many problems don't. Sometimes a system becomes stronger precisely because no single individual is indispensable. That's why termite colonies are so resilient. Lose one worker, the colony continues. Lose 1,000, the colony adapts. No single termite carries the future of the mound. The colony carries it together. Go back to the worker we met at the beginning. The one carrying a single pellet of soil. It never knew whether that pellet became part of a tunnel, a wall, or a ventilation shaft. It never understood the architecture surrounding it. It didn't need to. Its job wasn't to understand the masterpiece. Its job was to leave the environment slightly different from how it found it. Then let the next worker continue. For tens of millions of years, that simple agreement has built some of the most sophisticated structures in the natural world. When the Harvard engineers built the Termites robots, they weren't teaching machines how to build. They were teaching machines how to cooperate, and that may be the more important invention, because the future of robotics, artificial intelligence, disaster response, space exploration, and perhaps even parts of human society may depend less on creating one machine that's brilliant and more on creating thousands that know just enough to help each other. The greatest lesson hidden inside a termite mound isn't about insects. It's about intelligence itself. Maybe intelligence was never something an individual possessed. Maybe it's something that emerges whenever enough simple parts begin following the right rules together. And that changes the question completely. The question is no longer who's in charge. The better question is what kind of system makes leadership unnecessary. That might be the most important thing termites ever taught us.